Ladies and gentlemen, welcome and thank you for joining us for today's press conference. This is the 7th year of the Future Science Prize, and today we're going to announce the 2022 laureates of the Life Science Prize, the Physical Science Prize, and the Mathematics and Computer Science Prize. Science is the commonwealth shared by all mankind. We expect to expand the influence of science by honoring outstanding scientists and their groundbreaking research work. Entrusted by the Donors Assembly of the Future Science Prize, the Supervisory Committee has observed the whole selection process of the Future Science Prize 2022. With credibility as the paramount concern, the Science Committee carefully selected candidates in strict accordance with the selection rules. The whole process regarding evaluation and voting process is all under scrutiny of the committee. After 8 months of meticulous evaluation, the winner list of the Future Science Prize in Life Science, Physical Science, and Mathematics and Computer Science is finally ascertained and will be formally announced today. Now, let me introduce Professor Douglas Nelson Chow Lin, who is the rotating chairman of the Science Committee of the Future Science Prize 2022, to give us an opening remark.
Good morning, ladies and gentlemen. Today is a big day for the Future Science Prize and also for the science-inspired general public around the world. After thorough analysis, extensive international consultations, and in-depth discussions over the past few months, we are very pleased to have reached an overwhelming consensus on the selection of this year's laureates. The 2022 winner list will be announced in just a few minutes. The Future Science Prize is a privately funded science award initiated by a group of scientists and entrepreneurs aiming to celebrate the accomplishments of scientists who have made outstanding contributions in Chinese mainland, Hong Kong, Macau, or Taiwan. There are 3 major categories at present, namely the Life Science Prize, the Physical Science Prize, the Mathematics and Computer Science Prize, with each award of $1 million respectively. The awarded research work must, 1, have made significant global impact, 2, be original with enduring importance or have passed the test of time, and 3, be completed primarily in Chinese mainland, Hong Kong, Macau, or Taiwan. There is no restriction on the laureate's nationality. Thanks to the diligent and dedicated effort of 23 members of the Science Committee, the 2022 laureates have been selected in recognition of their internationally acclaimed breakthroughs. With their insatiable curiosity, innate passion for exploration, determined drive to overcome obstacles, and tenacious commitment to the highest standard of science, the laureates have expanded the frontier of human knowledge in both macroscopic and microscopic worlds and ascertain some promising passageways in future ventures into uncharted domains. Their noble spirit, accomplishments, and contributions warrants the recognition of this award. Next, representative of the 3 prize committees will announce the laureates list and present summaries on the nature and impact of their contributions. Thank you.
Ladies and gentlemen, on behalf of the Life Science Prize Committee, we are excited to announce the winner of the 2022 Life Science Prize. 2022未来科学大奖生命科学奖授予李文辉，北京生命科学研究所、清华大学生物医学交叉研究院，奖励他发现了乙型和丁型肝炎病毒感染人的受体为钠离子牛磺胆酸共转运蛋白 NTCP， 有助于开发更有效的治疗乙型和丁型肝炎的药物。2022 Future Science Prize, Life Science Prize is awarded to Professor Wenhui Li from National Institute of Biological Sciences, Beijing, China, Tsinghua Institute of Multidisciplinary Biomedical Research, for his discovery of the hepatitis B and D virus receptor, sodium taurocholate cotransporting polypeptide, NTCP. This discovery facilitates the development of more effective treatment for hepatitis B and D. 2 billion people have been infected with HBV worldwide, causing approximately 1 million deaths per year. The identity of the HBV receptor was unknown. Wenhui Li identified the HBV receptor to be NTCP. HBV amyloid protein pre-S1 is critical for HBV infection. Using pre-S1 as a bait, Wenhui Li and his team, using a very unique biochemical approach, fishing out the HBV receptor from tissue to liver cell culture as NTCP. To further demonstrate NTCP is the receptor for HBV, Wenhui Li and his team performed 2 critical experiments. The first experiment is to silencing NTCP gene and demonstrate silencing NTCP inhibit HBV and HDV infection in hepatocyte cell culture. The second critical experiment is to transduce NTCP gene into non-susceptible cells. NTCP expression renders non-susceptible cell susceptible to viral infection. The discovery of NTCP as HBV and HDV receptor explained three long-standing mysteries in HBV research. First, it explained the species specificity. It also explains the susceptible population, and it explains the liver tissue specificity. The discovery of NTCP as HBV and HDV receptor helped scientists to establish the tissue culture system, animal model, and also provide new targets for drug development. The discovery of NTCP as HBV and HDV receptor has already provided key targets to develop new therapy for HBV and HDV treatment. There are two approaches. One is to reducing NTCP expression. The other approach is to design drugs to compete binding to the receptors. Thank you.
Ladies and gentlemen, on behalf of the Physical Science Prize Committee, we are excited to announce the winner of the 2022 Physical Science Prize 2022未来科学大奖物质科学奖授予杨学明，南方科技大学中国科学院大连化学物理研究所，奖励他研发新一代高分辨率和高灵敏度量子态分辨的交叉分子束科学仪器，揭示了化学反应中的量子共振现象和几何相位效应。2022 Future Science Prize Physical Science Prize is awarded to Professor Xueming Yang from Southern University of Science and Technology, Dalian Institute of Chemical Physics, Chinese Academy of Sciences, for developing new generation molecular beam techniques with high resolution and sensitivity for state-resolved reaction dynamic studies, revealing quantum resonances and geometric phase effects and chemical reactions. We all know chemical dynamics is foundational to chemical reactions, particularly for chemical industry, pharmaceutical industry, and indeed for everybody's daily life. There's billions of chemical reactions happening in our own body. And the transition state has been regarded as the holy grail of chemistry since 1935, the formulation of transition state theory, to 1967, when the Nobel Chemistry Prize was given to the study of fast chemical reactions initiated by rapid jumps due to temperature, pressure, and light photolysis. In 1986, the Nobel Chemistry Prize goes to the dynamics of chemical elemental processes, starting use cross-molecular beam technique. In the 1999 Nobel Prize on femtosecond spectroscopy to study transition state of chemical reactions. These are the foundational works to really show the transition state is the holy grail of chemistry. So classical transition state theory, showing in case 1 right here, showing that only the energy is higher than the energy barrier, then the reaction probability is 1. But for the quantum resonance transition state, when the energy is matching this quantum state, even though still below the top of these transition energy barriers, but there's a resonance right there showing up, and the energy of resonance, the probability of reaction is increased tremendously. So the technique to measure transition state of this quantum state is actually very, very challenging. One way to measure this a quantum state, quantum resonance, is really the N-ion photoelectron spectroscopy by measuring the kinetic energy ejected from these molecules and giving the input of photon energy. You can back calculate the transition state energy. Another technique was really developed by Professor Xueming Yang is to have a new generation of molecular beam techniques for quantum state resolved reaction dynamics. And Professor Yang developed this quantum state specific backward scattering spectroscopy method, which can measure the reaction resonance. The reason is it could reduce the averaging effect of this partial wave, can resolve individual quantum partial wave clearly. For example, back to about a decade ago, Professor Yang used this technique to measure the reaction between fluorine and hydrogen. And when the energy of the reaction was tuned, lining up with this transition quantum states, and he could observe this resonance peak right there, providing very clear evidence of quantum resonance for the transition state. And another important illustration of his contribution is he observed for the first time the geometric phase effect by using this quantum state resolved molecular beam techniques and these rim patterns of quantum states by mapping the velocity of deuterium by matching with theoretical simulation. He provides very clear evidence of geometric phase effect in the chemical dynamics. And another exciting work he demonstrated is to use quantum interference as a sensitive probe to the geometric phase effect and the low energy, the two different paths of this reaction, and providing the quantum interference, providing the signal to probe the geometric phase effect. A very exciting question in chemical dynamics is the spin-orbital interaction. How would that affect the chemical dynamics? Professor Yang used the spin orbital split partial waves, the quantum interference between them, to clearly illustrate the effect of a spin orbital interaction on the chemical dynamics. This is another important piece of contribution to the quantum resolved chemical dynamics. For the future, we believe this is really the starting point of quantum state resolved chemical dynamics. This will remain as the forefront of chemistry, will make a huge contribution to the understanding of chemical dynamics and really open up a whole new world of what quantum state will play in the chemical reactions. With that, I would like to thank you for everybody's attention.
Ladies and gentlemen, on behalf of Mathematics and Computer Science Prize Committee, we are excited to announce the winner of the 2022 Mathematics and Computer Science Prize 2022未来科学大奖数学与计算机科学奖授予穆一鸣，香港大学，奖励他创立了极小有理切线处理论，并运以解决代数几何领域的一系列猜想，以及对尺寸处上的 Ax-Schanuel 猜想的证明。2022 Future Science Prize, Mathematics and Computer Science Prize is awarded to Professor Ngaiming Mok from the University of Hong Kong for developing the theory of varieties of minimal rational tangents in algebraic geometry to solve several long-standing problems, and proving Ax-Schanuel's conjecture for Shimura varieties. Mok's work is on complex algebraic geometry, which is about algebraic varieties defined by algebraic equations. In one-dimension case, that's classified by three different types: the rational curves, elliptic curves, a high-genus curve. In high dimension, the variety being very complicated, but they are built up on three relatively simple varieties. They're called Fano varieties, Calabi-Yau varieties, a variety of general type. The Fano variety can be defined by equation which is smaller than variable, for example. Calabi-Yau variety is exactly the same number of variables. General types are more complicated. So the Fano variety are simplest in this category, but Fano variety itself has two different simple examples. One is defined by equations. For example, you start with a projective space, n-dimensional. Then you take some equations, f1 to fm. If you assume the sum of the degree is at most the number of the variables, then you get a Fano variety. Then another way to define a Fano variety is the simple Lie groups. You start with simple Lie group, you merge a Borel subgroup, then you get a Fano variety. And the second example, including the famous Grassmannians. Professor Mok and Professor Huang and his collaborator developed a theory called a variety of minimal rational tangents to study the Fano variety. The idea is that it starts with a point on the Fano variety, then you have many rational curves. Over the rational curves, you take so-called minimal rational curves, that the degree is minimal. Then you look at the tangents of the rational curves. Then you get a variety of the tangent variety, tangent bundles, projected tangent bundles, original variety. They have two important applications. The first application is about the rigidity. So we know that the projective space is rigid and algebraic deformation. So you cannot, you have one projective space, you don't have other projective space. It can move around. And Professor Mok and Professor Huang, in a series of papers 1998 to 2005, proved that the semi-rigidity works for a rational homogeneous space of Picard number 1. This is a rather difficult problem. It's a simple but rather difficult problem. The second application of their theory is solve a problem of lattice field about the maps from projective space. So we know the lattice field has a proof of theorem that if you have a finite morphism from a variety Pn to Y, then the second variety must isomorph the Pn. So that's a very surprising theorem. And he raised a question about the rational homogeneous space. And this is exactly solved by Huang and Mok. 1999, they used their VMRI. They say that, okay, so the same rigidity works for any rational homogeneous space. The conclusion is slightly different. So you either Y isomorphic the Pn or Y isomorphic X. The second work of Professor Mok is about the Schanuel's conjecture. We know Schanuel's conjecture is an important conjecture in number theory. It's about
the transcendental degree of numbers formed by exponential. So it starts with the number x1 to xn, then you take the exponential, you get a 2n of numbers. If you assume the original and top of the numbers are linearly independent, then the 2n numbers, the transcendental degree is at least n. So transcendental degree means the freedom. So for example, if you take one of the numbers 1, other number 2 pi I, then you get e and a pi. Then this conjecture say e and a pi algebraically independent. So this is, of course, it's a very difficult problem. It's still not solved. The work is about the hyperbolic version of the Ax-Schanuel's conjecture. So this the object of this thing is called a Shimura variety. The Shimura variety is a quotient of Hermitian symmetric space by a arithmetic subgroup. So in dimension 1 case, we know this uniformized by a unit disk. They usually called a modular curve or Shimura curve. In 2019, Professor Mok joined with Jonathan Piller of Oxford and Jack Zimmerman of University of Toronto, they show that the Ax-Schanuel conjecture works for Shimura variety. This is the important contribution to both number theory and algebraic geometry. In fact, after they proved their conjecture, people found immediately important applications in the zebra-pink conjecture and uniform model length conjecture. Thank you.
Congratulations to all the newly selected Future Science Prize laureates on this great honor. We're now bringing today's press conference to a close, and we look forward to seeing you in November at the award ceremony and Future Science Prize Week. Thank you.